2. From free motions to forced motions. Yeah. The previous one topic, that's the free motion case. Yeah. There is no forced part. There is no external force. Yeah, let me explain the difference. Yeah. Role of forcing function. Yeah. This time, we want to add forcing function to the system. Yeah. The previous one, there is no forcing function. Yeah. All right. So this time, let's look at this new modified system. Yeah. Similar to the old one, but you can see there is something new added, this part. Okay? Little r function, r of t. So what's that r of t? The function here, 2 arrows, up or down, that represent forcing function. Forcing function, the direction could be up or down. Okay? Yeah, the direction of the r function. Yeah. Positive, negative directions. Yeah. The free motion mass spring system. Yeah. Our previous one, the free motion one, homogeneous equation. Right hand side 0. There is no forcing function. No forcing function. Yeah. Homogeneous system. All right. So this means no external forces. Yeah. So we treat as the R part, we treat as the external force. Not internal. Internal, there are some forces, right? By Hooke's law, internal. Okay. Yeah. The string, that force, damping force, right? Yeah. Internal forces. Yeah. But here we look at the external forces. Yeah. No external forces, but only internal forces controlled the motion. Yeah. So that's the free motion type. Yeah. All right. Now we add external force, R of t function. Yeah. So our system becomes non-homogeneous system. Right hand side, we have R function. Could be positive, could be negative. Okay? 2 directions. All right. Yeah. All right. And this type we call the forced motion type. This equation, forced motion type, ODE. Yeah. All right. Then the name of R function. There are several names. If you see these different names, you know, they talk about the same thing. Forcing function, yeah, the first one. Second, input. Remember, we used input before. Yeah. Input, output. Yeah. In chapter 1, input. Yeah. Here, we can also use that input, R function. Or driving force. Yeah. Yeah. The R function, driving force. The solution, y of t function, yeah, we call it output. Yeah, that's in chapter 1. We did it. Yeah, output. Yeah, or response. Yeah, response. So in the interpretation, yeah, because you see this response frequently in the interpretation, so you know that's the y function. Response of the system to the driving force. Yeah. Because sometimes in the word problem, you see the wording like these things, the driving force response. Okay, so you know what they are talking about. Okay, yeah. All right. Then model resonance. Yeah. Because later we need to talk about this issue, resonance issue. Yeah. So that's one of the important problems. So engineers need to consider. Okay. So when you find a solution. So you need to consider the frequency related to this resonance thing. Yeah. So later we will do the calculation. Yeah. On the what frequency you get this resonance? What frequency you can avoid this resonance? Okay. All right. Yeah. So we need to model resonance. The resonance caused by periodic external forces. Must be external, okay? Yeah. For periodic, because only when you have periodic forces, you have frequencies, right? Yeah. Frequencies is determined by period of the force. Okay, so you have that period and the frequency. Yeah. All right. So the periodic external force, we use this expression. Yeah. Model. When we model, we use this expression. Okay? F0 times cosine of omega t. Yeah. That's the periodic external force. We put into that equation. All right. F0 positive, omega also positive. Okay. Yeah. All right. Then we consider non-homogeneous ODE. This model, this equation. We need to solve this equation. Okay? So our next question, how to solve this type of equations? Yeah. Yeah. Also, relatively simple. Yeah. So let's look at the solutions. Yeah. All right. Next, C.3 topic. Non-homogeneous second-order linear ODEs. We want to look at the solution. Oh, question? Yeah, yeah, I realized that. Yeah, several students. Yeah, need to. Yeah, so let me. Yeah, so that's the system we want to solve. Yeah, so we will look at the solution. Yeah, yeah. Actually, regarding the solution, so you will see we did half of it. Yeah, we did half of it. Yeah. Homogeneous general solution, that's the half of it. Yeah. The other half, remember particular solution. If we can find just the one particular solution, then we get all solutions. That's simple. So we only need to focus on the particular solution part. Okay? How to find a particular solution? Yeah. So our new topic, find a particular solution. All right, so let's start. Yeah. C.3. Yeah. Non-homogeneous second-order linear ODEs. Yeah. Here we talk about, general idea. Yeah. After that, then we look at the, solutions. Yeah. Non-homogeneous second-order linear ODE. So this time we consider the standard form like that. Yeah. R of t cannot be identical to 0. Yeah. Otherwise, homogeneous case, we already, homogeneous case, yeah. 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 All right. Yeah. Yeah. Yeah, homogeneous case, we have part of the solutions. Yeah, because for P function, Q function, for the arbitrary P function, Q function, still not easy to solve. Yeah. All right. So the general solution, when we look at the general solution for this non-homogeneous system, we can write it sum of two types of functions. Yeah, here. YH, YP. YH refers to homogeneous general solution. Yeah? Because if we replace R function by 0, we can solve a homogeneous system. Okay? So that's the YH part. YP, particular solution. Particular solution for this non-homogeneous. Yeah. All right. So YP, any particular solution. Only one. We only need one. All right? And YH, C1Y1 plus C2Y2, the general solution for the homogeneous, corresponding homogeneous equation. Yeah. So if we can find a solution, yeah. If we can find a solution, yeah. Okay. All right. Yeah. Yeah. So a general solution of non-homogeneous ODE includes all solutions. Yeah. So here, this statement tells us the general solution. If you can find one particular solution, and also the general solution of the corresponding homogeneous equation, yeah, then this general solution covers all solutions for the original non-homogeneous equation. Yeah? That's a, special property for this one. That means there is no singular solution. If you connect to last time we discussed singular solution, there is no singular solution. Yeah. Singular solution, we know it cannot be covered by any general solution. That's what we call a singular solution. But for this particular equation, it's so special, there is no singular solution. Yeah. If you recall the first order ODE, first order, yeah, last time I also asked you, but I forgot the name. Now, later I remember logistic equation. Logistic equation, yeah. If you look at the logistic equation, there is a singular solution. Y equals 0 is the singular solution. Logistic equation. Y prime equals AY minus BY squared. That's the logistic equation. Okay? Yeah. Y prime, first order, Y prime equals capital AY minus capital B times Y squared. So that form we call a logistic equation. We use it to model population growth. Yeah. That one, we can write a general formula. Okay? There is a general formula. Okay? 1 over some function. Okay? 1 over denominator, with constant term and E term, 2 terms at denominator. Constant term, A over B, then there is a E term. Yeah. You can see this general solution cannot be 0, right? Because numerator 1 over denominator can never be 0. Yeah. So the general solution cannot be 0. But Y equals 0, it is a special solution. Y prime equals AY times minus BY squared. Y equals 0 must be a solution. So that's a singular solution. That is a singular solution. But here, second order, non-homogeneous, there is no singular solution. How special it is. Okay? Yeah, so that's the property. All right. Yeah, here, yeah, you can see we spend a lot of time talking about the properties, concepts. Yeah. So you will expect, so in quizzes, homework assignments, tests, yeah, you have, about 1/2 of the questions about these properties. Okay? Pretty much about 1/2 questions. Yeah. Because I like you have good understanding. Okay? Other than you can do calculations, but conceptually, you have good understanding. Yeah. That's also important. Yeah. All right. Question. How to find solution y little p particular solution. Yes. Yeah. That's something, we asked before. Yeah. This time, there is some methods we can apply to find particular solution. Yeah. Yeah. All right. Yeah. So this chapter, there are two methods we can use to find particular solution. Yeah. The first one, we will see soon. Yeah. Simpler one. One simpler. Yeah. Second one, the other more general. Yeah. But much harder. Okay. Harder than the first one. Yeah. Yeah. All right. The idea. So let me talk about the idea of the first method. The name of the method is called method of undetermined coefficients. Yeah. 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 So the idea is very simple. Very simple. Yeah. First, we guess the solution, the structure of the solution. We make a guess. Yeah. But it's not a random guess. Okay? It's not a random guess. From the equation, we can have a, good clues. We can find some good clues to help us make the right guess. Yeah. Guess the structure of the particular solution. The structure is right. We did that before, remember? Yeah. We did that about E function, so we guess that's the structure. So we use that E function before. Yeah. Here, the same thing we will do. We make a guess for the structure of this particular solution. But after we guess the structure, we need to put an undetermined coefficient with it. Yeah. Because the coefficient number we can change. That freedom is useful. Yeah. When we change the coefficient number up or down, when we can find the right place, right point, then the whole equation holds. That's the simple idea. Okay? Yeah. So that coefficient allows us to do an adjustment. Yeah. That's interesting. Very simple idea. Yeah. All right. But this method can only be used for constant coefficients. Constant P, constant Q. Yeah. If it's not constant, no, it does not work. Okay? Yeah, so that's why it's very restrictive. Yeah. But for constant, that mass spring system. Okay? So we can work on that mass spring system. That's constant. Yeah. Yeah. So many engineering problems, we just need a constant coefficients. All right, yeah. So simplified form. Yeah. So here, let me write simplified form. Yeah. Like that. Yeah. All right. Now this R function should be special functions. Then we can apply this method. If R function is very bad, then we cannot apply. Okay? Yeah. R function must be several special, nice functions. Okay? Nice functions. Yeah. All right. So what's that? So let me list R function type. Yeah. All right. When R, sorry, I forgot to type R. Okay? Yeah. So when R, here, R of t, okay? Yeah. R of t, the first case, exponential function. R of t that's the first case, comma. We have several other cases. Okay? Second, a power of x. X to certain power. Yeah. Power function. A cosine or sine function. So all nice functions. Yeah, you can see. Yeah. All right. Or sums or products of such functions. See? Yeah. Yeah. Then we can apply this simple method. Okay? Yeah. Yeah. Otherwise, yeah. So we have to try different methods. Yeah. Okay? Yeah. All right. Yeah. These functions have why this method works for these functions, because this property. These functions have derivatives similar to itself. Right? Yeah. Exponential function derivative similar to itself, right? Yeah. Power function derivative also power function but lower order, right? Yeah. Sine cosine derivative also sine cosine sine, just switch, but we know same type. Yeah. 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 Some angle, shift a little bit. Yeah. Yeah. The property. Yeah. So then we can apply this simple method. Yeah. All right. Yeah. Okay. Now let me show you this method. Yeah. I want to use a simple example to show you. Yeah. So C.4, method of undetermined coefficients. Yeah. This method. Yeah. All right. All right. Input exponential function. Yeah, this time. Yeah. Actually, there are three cases. Yeah, three cases. This one, exponential function case, and a power function case, and a cosine function case. Yeah, three cases. Yeah. Yeah, but in this C.4, I only show you this case. Yeah. In the next section, next topic, C.5, then I show you, remaining other cases. Yeah. All right. Yeah. Let's look at this example. Solve the initial value problem. Yeah. Equation, yeah. Constant coefficients, left-hand side, right-hand side, exponential function. Follows the pattern, yeah. So we can apply method of undetermined coefficients and initial conditions. These two initial conditions. Okay, all right. Yeah. Now, based on the idea, remember. So I talk about that idea. So now, we do the calculation. Find a particular solution yp, the first step. Second step, the general solution. The second step, pretty easy. Yeah. The hard part, relatively hard part, the first step, yp. Yeah. All right. Then for yp, here, yeah. Look at that, this structure. Yeah. Here, we need some experience. Yeah. Why we let this yp equals capital C? The C is the undetermined coefficient. Okay? Yeah. That's so-called undetermined coefficient. Because that capital C will be determined. Yeah. At the end, we need to determine this capital C. Yeah. Yeah. All right. But the question is, how do you know? You can guess like this. X squared times e to the negative 1.5x. E to the 1.5x, that's fine, right? E to the 1.5x, that's fine. Because from our function, you can have the e structure. Yeah. But how about x squared part? Yeah, 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 yeah. The reason, not too hard to understand, yeah, because we think about we need to take first derivative, second derivative. Yeah. So you have x squared, think about first derivative, second derivative, right? Yeah. So by the product rule, right? Yeah, derivative product rule. Yeah. So you have, polynomial times e function. Yeah. So you have a polynomial part. Yeah. E function, that's the common factor, so we can cancel out. Yeah. So we only have a quadratic polynomial. So if you use this structure, we just do calculation on a quadratic polynomial. Then we can handle quadratic, not hard. Yeah. Okay, yeah. So let's do the calculation. First, yp prime, so you can find the derivative, yeah, carefully, yeah. So you can see you get a quadratic polynomial times e function. Yeah. So that same e term, so we don't worry, we can cancel this term later. Yeah. Yp double prime, yeah, another quadratic function times e. See? Yeah. That structure, quadratic. Okay? Yeah. Yeah. So you can see order 2, second order, then we should consider the quadratic case. Yeah. Third order, we should consider the cubic case. First order, linear case. Yeah. That logic. Then, substitution. Yeah. Then we get this equation. E cancel out. E function, E term canceled out. Okay? It's gone. Yeah. Then remaining quadratic equation. Yeah. Capital C to be determined. Yeah. How to determine capital C? Yeah. I think you have no problem to determine capital C, right? Yeah. The calculation, yeah, combine the terms. Yeah. What is the coefficient of x squared? What is the coefficient of x? What is the constant expression in C? Yeah. And all these coefficients, yeah, if you write a standard quadratic equation formula, all coefficient must be 0, right? Yeah. All coefficient must be 0. Yeah. Yeah. All right. Yeah. So let's see. Yeah. All right. Yeah. So let me do some simplification work first. All right. All right. First, let's look at the x squared term. X squared term. Yeah. Left, both sides, x squared term. Left-hand side, x squared, we have this term, 2.25c. This term, also 2.25c. That's the positive coefficient, these two terms. So we add these two numbers, we get 4.5c, right? Yeah. 4.5c yeah. Then the negative part, 3 times 1.5, 3c times 1.5, that's also 4.5, right? 4.5c x squared. So this term is gone, is 0. Okay? X squared term is gone, 0. Yeah. All right. Then x term. Let's look at the x term. X term, because this is gone, this is gone. Yeah. This is gone. All right. Yeah. x term minus 6c here plus 6c, yeah. So we have 6c minus 6c, right? Also 0. Okay? The x term also gone, right? Yeah. Plus minus. Yeah. All right. Then the constant term. Now, then it cannot be 0 because right hand side is negative 10. Okay? Right hand side negative 10. Left hand side, because x term is gone. Okay? X term is gone. Only 2c left. Yeah. 2c left. 2 capital C equals negative 10. So c equals negative 5. Capital C. So it is determined. Yeah. So that's what we call method of undetermined coefficient. Yeah. And by this equation, we determine it. Yeah. Question. May not be. Right. Yeah. Yeah. Right. If they don't, no solution. No. Yeah, because if not cancel out. If not cancel out, so the capital C must be 0. Yeah. Yeah, because some non-zero number times C. All right. Yeah. Capital C must be 0. Look at, if you use capital C, do you get a contradiction other places? If you get contradiction to other places, that means your first assumption is wrong. Okay? The structure, your first assumption is wrong. If your structure is correct, then it's very likely, compatible. Okay? If the structure is right, everything fits in a perfect way. Okay? Yeah, because the structure determines everything. Okay? If only the structure is correct. Yeah. If cannot be canceled, that means your first step, your structure assumption is completely wrong. You have to modify your structure. Yeah. You have to modify your structure. Okay? Yeah. 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 Because this method, this method only when all the conditions, all the patterns, all satisfied, then you can apply. Okay? Yeah. If one little tiny piece is wrong, it won't work. Yeah. It won't work. Yeah. Yeah. But yeah, just think in this way. Yeah. Everything is determined by the structure. If you get the right structure, yeah, you can get everything correctly. Yeah. All right. Yeah. So let's look at the remaining of the solution by comparing the, we just did that, right? Comparing the coefficients. C equals negative 5. Yeah. So we can write YP explicitly. Okay? Yeah. Then we need to write YH. Yeah. Look at the homogeneous. We need to write YH. YH, we need to solve this characteristic equation. It's simple. Yeah. The solution, double root, lambda equals negative 1.5, but it's a double root. Double root, we know its solution. Yeah, there is a special format for its solution. That's like this. Yeah. This general solution: C1, C2, X. Yeah. This. There. The particular solution part. Yeah. So that's the general solution for the non-homogeneous original equation. No. Non-homogeneous equation. And when we find this general solution, we do not look at the initial conditions. Yeah. Yeah. We do not look at initial conditions. Yeah. Only after we have the expression of the general solution to determine little c1, little c2, then we apply initial conditions. When x equals 0, x equals 0, this term is gone. Okay? Yeah. Last term is gone. X equals to 0, this term also gone. Okay? All right? Yeah. C1, E term is 1. E term is 1. Okay? C1 times 1 equals Y value 1. So C1 is 1. Yeah. You find C1. But C2, a little harder. C2, you need to take derivative of Y, then plug in X equals 0. Yeah. Derivative, a little harder to calculate. Yeah. All right. Carefully, calculate. Yeah. So then plug in, because you already have C1. C1 is known, so you need to find a C2 value. Yeah. Here, I just write out the final solution. Yeah. All right. By the initial conditions, Y equals this representation. Okay? C1, C2. Yeah. That's this method. Okay? Yeah. R function is exponential function. Yeah. For other functions, similar idea. Yeah. Similar idea. Yeah. Yeah. But the computation could be harder. Yeah. Especially for sine cosine. Yeah. Computation. Yeah. A little harder. Yeah. Yeah. All right. Yeah. Okay. Yeah. So that's so at least so you know how to work on these questions. Yeah. All right. Next one. Yeah. 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 I think this should be C.5. Yeah. Modeling of forced oscillations, and at the same time we need to look at this problem, resonance problem. Yeah. All right. So let me give you an application question. Yeah. Our problem number 9, undamped forced oscillation with resonance. Yeah. Undamped. Yeah. Undamped, you know, the middle term is gone. Okay? Yeah, the damping term, the Y prime term is gone. Yeah. All right. So let's look at the question first. Yeah. Yeah. The system. Yeah. This system. Yeah. We saw it before. Find the motion of mass spring system in the figure with mass equals 0.125 kilogram. Damping 0. Yeah. Damping force 0. Spring constant 1.125 kg over / second square, and the driving force cosine T minus 4 sine T. The unit is Newton, NT, Newton. The force unit, Newton. Okay? Yeah. All right. Assuming 0 initial displacement and velocity. Initial value conditions. Initial conditions. Yeah. Then, for what frequency of the driving force would you get resonance? Yeah. Yeah. Actually, 2 parts. The first, let's find the solution. Yeah. Because the first part, let's find the solution is Y function displacement, right? Yeah. Second, for the second question, we need to understand what do we need to do for the second question. For what frequency of the driving force? Because here, the frequency of the driving force, here, can you see what's the frequency of the driving force here? What's the frequency of driving force? Based on the definition of frequency. First, what's the period of driving force? What's the period? 2 pi, right? What's the frequency? Period is 2 pi. What's the frequency? Here, omega is 1, right? See? Omega t, right? our force function, usually we are given omega t, but omega is 1. Omega is 1, okay? Yeah. So what is the frequency? 1 over 2 pi. Reciprocal of period, right? Reciprocal of period. So 1 over 2 pi. Yeah. Yeah. So this force, the frequency is given, yeah. But for this question, what frequency of the driving force? That means we need to put omega back, okay? Yeah. Because the omega won't be this one, all right? Because we need to calculate that omega for the resonance, yeah. You know, omega. That point, yeah, causing the resonance. Yeah. 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 What's that? So you may, yes. So here you need, under what situation the resonance occurs for the omega? Yeah. The situation is like this. Yeah. Because when you find a y solution, you know, because at the end you need to find a y solution, yt, right? You know, some expression. You know, some expression could be very complicated. Okay? All right. There, in your expression, there is some fraction expression. Okay? Some fraction expression. In that fraction expression, there is a part about omega squared minus omega 0 squared. Yeah. Something like that. Okay? At a denominator. There you can see when the omega is very close to omega 0, the determinant close to 0, that means this displacement is, you know, very large, right? Some number over 0, close to 0, very large, crashed, right? The system, you know, crashed. The resonance caused. Okay? External force make the system, you know, crash. Yeah. Yeah. So for engineers, very important, because when you design bridge, there is a frequency. There is a natural frequency of the bridge, right? Natural frequency. Okay? The bridge, you know. Yeah. But then, when you consider external force, okay? You know, a group of people walking on the bridge with the same frequency. How about that? Same frequency. Okay? People walk in the same pace. Okay? Yeah. Same pace. So frequency the same. If that frequency happens to be the same frequency as the natural frequency, what would happen? Yeah. So that's why when people walking through a bridge, you know, do not walk at the same pace. Okay? Yeah. You know, some random way. You know. Yeah. So do not cause any particular frequency. Yeah. That's external force. That's external force. Yeah. 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 So that problem. Yeah. Here, let's look at a solution. Yeah. So solution, you know, idea pretty simple. Yeah. Here. All right. First, set up equation, this one. Because the damping force 0, damping term is gone. Okay? Yeah. Middle damping term, y prime term is gone. Okay? So we have this equation. All right. Yeah. So then, M we know, K we also know. Yeah. Initial condition, yeah. Initial condition, displacement y of 0, displacement 0, velocity y prime of 0 also 0. Initial condition. Now we need to solve this equation. How to solve this equation? Okay. Yeah. Right hand side, it's a sine cosine. Yeah. Then when we guess the y function, how do you guess the y function? Do you want to guess the y function has the similar structure, sine, cosine? Because if your y function has similar structure, when you take derivative, you also get a y sine cosine. You take second derivative, you also get a y sine cosine. Right? Yeah? Yeah. So, all right. So when we want to find a particular solution. Yeah, because here, the hard part is the particular solution. Yeah. For the homogeneous solution, easy, very easy. Yeah. So we don't worry about the homogeneous solution. But particular solution is a little hard. Okay? Yeah. So we need to take YP has the similar pattern or structure, AB to be determined. The coefficient, this time, A coefficient and a B coefficient to be determined. Okay? Yeah. Yeah. All right. Then, with this structure, now you can calculate the derivative of YP. Yeah. You can expect some number times cosine, some number times sine. Okay? Also the same structure. Double prime, also another different expression times cosine, another some expression times sine. Yeah. All three things, you can put it back. When you compare left-hand side, right-hand side, can you compare the coefficient part? Both of cosine should be the same. The coefficient part of the sine should be the same. Two equations. Yeah, because compare cosine coefficient, you have first equation. Compare sine coefficient, you have the second. And you have two unknowns, two equations, so you can find these two values. A, B. Okay? Yeah. That's your general solution. Oh, sorry. That's your particular solution. Then you write a general solution with C1, C2. So then you find a C1, C2 value with these two initial conditions. Then you get a final solution. Okay? Yeah. But that one, just find the solution with a given force, right? Given periodic force. But to answer the second question, then we need to use that omega, put omega in, then we solve the problem. The general solution should be in the omega formula. Then you look at if the denominator could be 0. Yeah. For what omega, the denominator could be 0. That's the resonance frequency. Okay? Resonance omega. Yeah. From omega, you can calculate the frequency. Okay? Yeah. All right. So, yeah. So I haven't completed. Yeah. So So let's leave the second half. Yeah, to complete it. Yeah. When I do problem solving session, then I complete this. Okay. Problem solving session. Then I complete this resonance part. Yeah. All right. That's it. Yeah.